Hello, this is Dr. Ryan Johnson, and this is Introduction to Statistics. We're doing section 6.3 today. So our main research interest today is on donating blood and whether or not the number of people donating blood changed from 2002 to 2004. And then there's going to be an extra investigation at the end about men versus women. So, we have this survey from the General Social Survey, and we've seen that before. So you can follow that link if you want to, but we generally know that the General Social Survey tends to have good methods for how they do surveys. And so for exercise number 1, did the study make use of random sampling, random assignment, both, or neither? So there should be enough information in that first paragraph for you to be able to tell that if you kind of include your common sense. But if you're still not so sure, you can always read about the General Social Survey with that link. Okay, but don't spend too much time on that question. You should be able to kind of have a good sense of what it is doing there. Okay, then number 2, state the appropriate null and alternative hypotheses in words and in symbols to address the research question of whether Americans were more generous with blood donations in one of these years than the other. So think about what Greek letter should you have in your hypothesis for the symbolic way of describing that. It's the same Greek letter you saw when you're reading of 6.3 in the Zai book. Okay, so here's data from 2002 and 2004. For each year, calculate the conditional proportion of adult Americans sampled who donated blood in the previous 12 months. Use appropriate symbols to represent them. Also calculate the difference between these sample proportions. So there should be 3 numbers. The proportion looking at people from 2002, the proportion looking at people from 2004, and the difference between them. And then we'll take 2002 minus 2004. It's kind of backwards from the way we normally do it, but that's just the way the app was set up by default, and so we're just going with that. Okay, so then produce a segmented bar graph or mosaic plot to display the conditional proportions. And again, you can use any technology you want, or draw this on a piece of paper and take a picture and put it into your document for your answers, whatever you need to do. All right. Now, for number 5, use the multiple proportions applet, which there's a long URL right there. Or you could go from our canvas, click on applets, and then multiple proportions. And then they tell you how to enter the data. So for instance, you could enter the data in a 2x2 table and call this 210. 230, and 1152 and 1106, and you can label these groups. So this group is 2002, this group is 2004, and this group is donated, and this group is didn't. Never use 2 words with these things. It messes up the app. Use table, and so you can do that, or you could also just select the data, because this app is built for this textbook, and so it's blood. Now, I'm actually going to mess up my data so that all of my answers in this video are wrong, because I want you to use the app. I don't want you to just get the answers from watching me use the app. So I'm going to delete a couple of my data entries, and then use data. And now I have, I'm going to also delete some of these ones too. Use data. Okay. So I've deleted data. Don't do that. Don't do what I did, so that my answers will all be wrong. But I'm going to still go through all the motions of what you need to do on the app, so that helps if you're kind of need that watching someone else use the app first. So now to our key idea. Shuffling is an appropriate way to estimate p-value for comparing groups regardless of study design, observational or experiment, random assignment, or random sampling, or neither. Of course, the study design is very important in determining appropriate scope of conclusions. So study design is important for how we determine causation, generalization, stuff like that. But shuffling is a good way to determine the p-value. So we're going to click the Show Shuffle options, and I dare you to try to say that 5 times fast. So we'll do that, and we'll have to move over here. Okay. And we're going to, number of shuffles, we'll just do 1,000. And so we'll do that. Okay. So now my observed difference, different from yours, is negative 0.0522. So we'll come over here and negative 0.0522. Indicate how to find the p-value, so this is what we do. And then we'll probably do beyond. And so my p-value is approximately 0. I might simulate a couple more times just to see. It takes a little bit of time and do it a bigger one. All right, so I got out of 11,000 times, only once did I get a simulated scenario as extreme as my sample. So report the p-value would be that fraction. Based on this p-value, do the sample data provide much evidence that the population proportion who gave blood in 2002 differs from the population proportion who gave blood in 2004? Well, your answer might be different from mine, but remember we're using the 0.05 criterion for the p-value. So make your decision based on that, just like we've been doing. Now, does the null distribution of the simulated values appear to follow an approximately normal distribution centered around what value? Also report the standard deviation of these values. So it's yes, it's following kind of a bell-shaped curve with mine is centered at 0 and my standard deviation's that number. So I would report those. How many standard deviations? Wait, let's see. I got ahead of myself. Okay, so number 8. Let's see what the standardized statistic tells us. So report the observed value in the sample for the statistic. And so report my observed value. So that'd be this number. The observed value is the observed difference. Okay, how many standard deviations? Based on your answer to question 7. So then to calculate how many standard deviations, you could, in your calculator, you could take, let's see here, you would take your observed difference. So my observed difference is negative 0.0522, and if I divide that by the standard deviation of the null distribution, which is divided by minus 0.014, so divided by 0.014, I get 3.7. So that's how many standard deviations? 3.7. Okay, and then do you remember we have that table of standardized statistics that tells us when strength of evidence is moderate, strong, or very strong. And so I would use that table, and in my case, mine is very strong, but yours might be different. Okay, now we're going to click the overlay normal distribution. And is the behavior of the two distributions similar? How do the p-values compare? It follows really well, so they are quite similar. And my p-value is almost the same, just a little bit off. Okay, so then check the box to compute 95% confidence interval. Okay. I forgot where that is. Is that over here? Yeah. So check the box to compute the confidence interval. Okay. Report the endpoints of this interval. So I would say, I'll give my answer, I'll give these two numbers right there, and then interpret this interval. So to interpret the interval, I would say we are 95% confident that the true difference of blood donors from 2002 to 2004 is between negative 0.079 and negative 0.025 people. And since it's really a ratio of who's giving, I could change those to percentages too. So I could say we're 95% confident that the difference in people giving blood between 2002 and 2004 is, if it changes those percentages, it'd be like negative 7.9% and negative 2.5%. Okay, because percent means divided by 100, so hundredths, and so you just move the decimal place 2 points for the percentages. All right. Does this interval contain only negative values, only positive values, or does the interval include the value 0 as well as both positive and negative values? So your answer might be different from mine. Mine is only negative. Another applet that can compute the p-values and confidence intervals for tested two proportions is the theory-based inference applet. So we're going to get the theory-based applet out. So back in our applets here, the theory-based one is over here on the right on the top. So we'll get that one out. Scenario, two proportions. And then I wonder if I could just, for me, because I want to use my made up data, I'm going to go over here. And so you guys could just put in your numbers here, your counts, your sample size of both groups, your counts, your p-hats. But I might try just doing this. Includes header. And then use data. Okay, stacked. There we go. Okay. So I'm still getting the same number there, so that's a good double check there. Make sure you're getting the same difference as your last app. Okay. So again, I have the wrong number there though. So all right. So then let's see, calculate. Test of significance. Okay, too many things open. So there we go. There's my test of significance. Make it match the null and alternative hypothesis. Okay. And so then verify the p-value you obtained earlier. So I get the same p-value. So like the answer to this question for me would be yes, it is still 0.0002 for me. Yours will be a different number. Okay, so that's what it means verify. It means like, yep, same number. All right. Then validity conditions. So as with single proportion, the theory-based inference approach for comparing two proportions is only valid when a normal distribution provides a good approximation. Conservatively, the theory-based significance test and confidence interval work well when there are at least 10 observations in each of the 4 cells of the two-way table. So if I look here, is there a way to show the table? No, not here, but in the other one there was. I could show table, and so as long as these 4 numbers right here are all at least 10, then I meet the validity conditions. Okay. So let's restate it here. The theory-based test interval for the difference in two proportions, called the two-sample z-test, or interval, work well when there are at least 10 observations each of the 4 cells. Okay? So each of these 4. Boom, 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 boom. Those 4. All right. So is it valid to use theory-based approach for 2 proportions in the study? For me, the answer is yes. Number 13, is it reasonable to generalize your conclusions from this analysis to the population of all adult Americans? Explain why or why not. That goes back to the methods of the survey. So was it a random sample? Okay, exploring further. Let's see what happens if we switch which is group 1 and which is group 2. Before doing any calculations, what do you think would happen to the standardized statistic, p-value, and confidence interval if you enter the 2004 sample as group 1 and the 2002 sample as group 2? So, this is a question where it's best to just, we're just looking for you to guess. This is not going to be, this part of the question is just greater than completion because we just want you to guess. Okay, so make this change in the theory-based inference applet. I switched the roles of group 1 and group 2. So one way to do that for me would be to do there. Okay, by clicking on it, I changed the success. I changed the way it's calculated. All right, and then press calculate. Oh, I'm in the wrong app. I want to be over here. Okay, so change group 2 minus group 1 and calculate. Okay, and so report the new values of standardized statistic, p-value, and confidence interval. So report your standardized statistic, that's your z-score, your p-value, that's this number, and your confidence interval. So, oh yeah, I want to do confidence interval 2. Okay. So notice that my p-value did not change, but my z-score, my standardized statistic, was negative and now it's positive, and my confidence interval was negative numbers and now it's positive numbers. Okay, so part C is just, was your guess right or was it wrong? Okay. Now, using the General Social Survey data to classify response by sex and combining the years 2002-2004, we construct a two-way table. So here's donated blood in the past year. There's male and female. So analyze these data to address the questions of whether American men and women differ with regard to donating blood. And so now you're going to go through everything again, just on your own this time. And so that'll complete section 6.3.